This is Professor Dare of Science, numbers. The first set of numbers to look at is the natural numbers. They're the basic counting numbers. Start with 1, 2, 3, 4, 5, etc. It's our first concept of quantity. We can count on our fingers. The set symbol is a script N. Within the natural numbers, there are prime and composite numbers. Prime numbers are natural numbers whose only factors are themselves and 1. And numbers that are not prime are called composite. Here's some composite numbers, 4, 6, 8, 9, etc. 6 can be written as 2 times 3. The prime numbers, each one of them, cannot be further factored except for multiplying it by 1, which any number multiplying by 1 doesn't change it, so that's not significant. Two numbers, 0 and 1, are considered to be neither prime nor composite. Every single natural number has a unique prime factorization. You can factor it and break it down into prime factors. And in the final result, use exponent notation for prime factors that appear more than once. 8, 2 times 4, and 4 is 2 times 2, that's 2 to the third. 28, 4 times 7, 4 is 2 times 2, 2 squared times 7, 150. Doesn't matter how you break it down, eventually you're going to end up with the primes. 6 times 25, 6 is 2 times 3, 25 is 5 squared. There are the unique prime factorizations for those composite numbers. Visually, prime numbers are one-dimensional and composite numbers are two-dimensional because they involve 2 or more. I should say, instead of two-dimensional, they're multi-dimensional. They have 2 or more factors. 6 is 2 times 3. This visual here shows 2 rows of 3 items each. So it's like a two-dimensional. 8 is 2 times 4. There's 2 rows of 4 each. And 7 is just 1 row of 7. There's no breaking it apart in any natural way. 7 times 1. If we had 2 times 3 times 5 squared, that would be interesting. How would we represent 2 times 3 times 5 squared? That's quite challenging. That would be three-dimensional, I suppose. It'd be 2 times 3, and then you'd have to stack those up into a 3D kind of a diagram. So that's the idea here. One-dimensional, two-dimensional, three-dimensional. It's just a way of visualizing the difference between prime numbers and composite numbers. Next, throw in 0 to the natural number set, and you get a new set called the whole numbers. Putting 0 in there enables subtraction to make sense. 3 minus 3 is now something. It's 0. It's nothing, but it's something. And the set symbol is a script W, whole numbers. Integers. Those are the whole numbers, and then you take also the negatives. So with every positive number, you have its negative. This enables additive inverses. 5 plus -5 is 0. Plus or minus reminds us of the set of integers. The set symbol is a script Z. Even and odd numbers. An even number is an integer a such that it can be rewritten as 2 times some other integer n. For example, 6 can be written as 2 times 3. An odd number is not even, and more specifically, it can be written as 2 times another integer plus 1. So you take an even number and add 1 to it, and you'll have an odd number. Example of an odd number, -5, is 2 times -3, which is -6, plus 1. Visually, an odd number has an extra 1 left over, and everything else is paired. Comes in 2s. So many 2s and a 1 left over. Here this evening, even 4 is just pairs of 2s. 2 pairs of 2s. Odd is something odd left over. Rational numbers are ratios of 2 integers, a over b. A is the numerator, b is the denominator. It's considered to be proper if a is strictly less than b. Otherwise, it's improper. And it's reduced if a and b have no common factor. Some examples of rational numbers in this list here. Notice that 5 can be written as 5 over 1, and 1 can be written as 4 over 4, or 3 over 3. And 0 over anything, including 10, is 0. So all these are rational numbers that can be written as a ratio of 2 integers. Denominators are not allowed to be 0. That's undefined. The 0 denominator is not defined. Can't have them. A fraction, a over b, is the same as a divided by b. The division symbol right here looks like a small fraction. There's a fraction bar, a top, and a bottom. That's not by accident. And a divided by b is the same as a times 1 over b, and that's the same as a over 1 times 1 over b. Having fractions enables multiplicative inverses. You can multiply 7 by 1 over 7 and get 1. The set symbol for rational numbers is script Q. Here are some examples of different types of fractions and their representations. Proper fractions up here, improper. Mixed is where you have a whole number part and then you add on a fraction part, which represents 3 plus 2/7. It's read 3 and 2/7. And it's equivalent to 23/7, but the mixed fraction is here. A reduced fraction is simplified. Take out the common factors. In this case, you factor 4 times 5, 5 times 5, and then the 5s can take out, and you have 4/5. You can go in the other direction. Instead of reducing, you can zoom them or expand them. For a purpose, 2/3 plus 1/4, in order to add them, they have to have the same denominator. Make the denominator 12 because 3 times 4 is 12. That is the least common denominator between 3 and 4. It's not always the product, could be smaller than the product. Anyway, 12 is a LCD. When you zoom a fraction, you have to do whatever you do to the bottom, you have to do the same thing to the top. 3 got zoomed by a factor of 4, so you have to do the same thing with the 2. 2 times 4 is 8. 4 times 3 is 12. 1 times 3 is 3. Now you can add them. They have the same denominator, 11/12. Fractions, when you convert them to decimal form, can be a terminating or exact decimal like 1/8, which is 0.125, or it can be an infinitely repeating decimal, such as 1/3, which is 0.33, and the dot, dot, dot means it just continues 3333, and a shorthand notation for that is using a bar over the repeating part. So this is 0, 0.33, showing that the 3's repeat. You could have just put 1 bar over the last 3. The 3 repeats, but it's the same to say it like this. Percent. 1/4 can be written as 25 hundredths, that's zooming it, and hundredths is percent, so that's 25%. The placement of a sign in a fraction, you can freely move the sign from the front to the top to the bottom without changing the value of the fraction. Irrational numbers, they cannot be represented as a ratio of 2 integers. 3 examples of irrational numbers: pi, the ratio of the circumference to the diameter in every circle; e, the limit as n approaches infinity of this 1 plus 1 over n to the nth power series; the square root of 2, which is the length of the unit square diagonal as shown in the picture here. If you use the Pythagorean theorem on this unit square, you'll find that the hypotenuse, the diagonal, is the square root of 2. Those are all irrational numbers. They cannot be written as a ratio of 2 integers. Converting them to decimal form means they go on forever. They do not terminate and they do not repeat. We did that down here. Here's pi. And you can approximate it, round it off to 4 decimal places. E equal to this, and round it off, and the square root of 2. But they, in actuality, go on forever and ever, and with no repetition. That's quite amazing in itself. The set symbol for the irrational numbers is the complement of the rational numbers, q prime, or set of real numbers, subtract, take out the rational numbers. The real numbers are made up of the union of the rational numbers union with the irrational numbers. And the set symbol for the real numbers is a script R. The real numbers contains the rational numbers as a proper subset, which contains the integers, which contains the whole numbers, which contains the natural numbers, and the real numbers also contains the irrational numbers, and the rational and irrational numbers are mutually exclusive. Their intersection is the null set. There's a variety of numbers involved in the real number world. Complex numbers. Numbers of the form a plus b times little I, where a and b are real numbers, and little I is not a real number, it's a square root of -1. A is called the real part, and b is called the imaginary part of this complex number. These numbers occur naturally when solving quadratic equations of the form, standard form, ax squared plus bx plus c equals 0, using the quadratic formula. Because the quadratic formula, notice, has in it the plus or minus square root. And if this b squared minus 4ac discriminant is negative, then complex numbers will come out as part of the solution. The set symbol for complex numbers is a script C, and C contains, as a proper subset, the real numbers, where the real numbers, b, the imaginary part, is 0, so you just have the a. Little I being the square root of -1, if you square it, you get -1. You cube it, you get -I. And if you put it to the 4th power, you get 1. And after that, this pattern repeats. This pattern of 4 things. So if we have I to the 13th power, for example, we can rewrite that as I to the 12th times I to the 12th is I to the 4th to the 3rd power, and then of course times I to the 4th is 1 to the 3rd power times I, and you just get I. So knowing this little foursome here, you can quickly figure out what any power of I is equal to. Every complex number a plus bi has what's known as a conjugate of it, a minus bi. They're mutual conjugates of each other. If you multiply conjugates together and work it out, this would be the difference of two squares, a squared minus bi squared. That's a squared minus b squared I squared. That's a squared minus b squared. I squared is -1. Negative times negative is a positive. So when you multiply the conjugates, you get a squared plus b squared. Because of the I being squared, a difference of two squares comes out to be a sum of the squares of the real and imaginary parts. Base 10 representation of numbers. Our decimal numbers are represented in base 10 notation. It uses one decimal point with whole parts to its left and fractional parts to its right. It uses 10 digits, 0, 1 through 9. Every position represents a non-negative on the left side or negative on the right side power of 10. Left side and right side relative to the decimal point. For example, 123.406 is 1 times 10 squared plus 2 times 10 to the first power plus 3 times 10 to the 0 power. By the way, anything to the 0 power is 1 by definition. Plus, now we're on the other side of the decimal point, 4 times 10 to the -1 plus 0 times 10 to the -2 plus 6 times 10 to the -3. Writing out what each of those are equal to, this becomes 100 plus 20 plus 3 plus 4 tenths plus 0 hundredths plus 6 thousandths. That's the meaning of this succinct decimal notation. Base 2 representation. Computer hardware represents numbers internally using base 2, known as binary, on and off notation, being electrical, on voltage, high voltage versus low voltage can store on and off states. It uses one binary point with whole parts to its left and fractional parts to its right. It uses two binary digits, also called in computer world bits, 0 and 1. Every position represents a non-negative on the left side of the binary point or negative to the right side, power of 2. Here's an example, binary number 1010.011. That means 1 times 2 to the 3rd plus 0 times 2 squared plus 1 times 2 to the 1st plus 0 times 2 to the 0 power. And then the dot is implied right here, plus 0 times 2 to the -1 plus 1 times 2 to the -2 plus 1 times 2 to the -3. When we take the values of these, that becomes 8 plus 0 plus 2 plus 0 plus 0 over 2 plus 1 over 4 plus 1 over 8. And if you add those all together, you get 10.375 base 10 equivalent. But there it is, base 2 can be stored and computed in computer hardware. Scientific notation. It's used to represent very small and very large quantities. It expresses a number as m times, this x here is a special x, it means multiplication, times 10 to the nth power, where m, its absolute value, has to be between 1 inclusive and 10 exclusive. Examples: the mass of an electron, and this is approximation here with the precision being rounded to 3 decimal points, 9.109 times 10 to the negative 31st kilograms. Remember, a negative exponent means 1 over 10 to the positive 31. It's a very small, these negative exponents, and it should be small. It's the mass of an electron. The mass of the Earth, 5.972 times 10 to the 24th power kilograms. Interesting how they would go about weighing these two objects. How many electrons would it take to equal the mass of the Earth? It would be the mass of the Earth divided by the mass of an electron, dividing these two decimal parts here that do not involve exponents, you get approximately 0.6556, and then using the quotient rule on exponents with like bases, 24 minus 31 is 24 minus a minus 31, because you subtract, is the same as 24 plus 31, 10 to the 55th power. But to get this in scientific notation, we have to shift this decimal over 1 to the right, which means we have to multiply by 10 to the negative 1 to compensate. And we have this now, and these two, we can use a product rule of exponents to add the exponents, and we end up with 6.556 times 10 to the 54th. That's how many electrons it would take to equal the mass of the Earth. So that tells you something, that 10 to the 54th is a really big number. And remember, it's got 54 zeros in the number. Be hard writing it down, you'd lose track how many zeros you'd written. Even if you put commas in, you'd start losing track of where you are. A very convenient notation, and also a computational notation that allows computations as was done right there. Quantities of chance. Probabilities represent chance or random events as numbers between 0 and 1 inclusive. The probability of an event A is indicated by the symbol capital P parentheses A. A probability of 0 corresponds to an impossible event. A probability of 1 corresponds to a certain event. The probability of an event A is equal to the number of outcomes that are favorable to A divided by the total number of possible outcomes. Example probabilities when rolling a single die. Probability of getting a 7 is 0. There's no 7s. Probability of getting a 1, 2, 3, 4, 5, or 6 is 100%. Probability of getting a 3 is 1 over 6, because there's only one 3 and there's 6 possible outcomes. That's approximately equal to 0.1666, 16.66%. Probability of an even number is 3 over 6, 50%. Same as the probability of rolling an odd number, 50%. Quantities of chance. Quantities of truth. Quantities of truth are used in formal logic, which involves Boolean algebra. The quantities used are true and false, which are commonly represented as T and F or 1 and 0. Some operations include and with this symbol, or with this other symbol, and not with this symbol. Here's a truth table. A Boolean variable A and B, possible combinations of their values, true, 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 false, false, true, and false, false. A and B results in true only if both A and B are true. Otherwise, it's false. A or B is true as long as at least one of them is true, and only false when neither of them is true. Not A reverses the truth value of A, so true becomes false and false becomes true.